Hello. Now we are in chapter 10 and we will study the mechanical properties of fluids. And let's go to the what are the topics in this chapter. The first we will go through the introduction, then pressure, then we will go through streamline flow, and then Bernoulli's principle, viscosity, surface tension. And I want to say that 70% of the Earth's surface is covered with water, and fluids are means if water is a fluid, as is a gas. Anything that can flow is a fluid. We will study the properties of fluids in this chapter, and we will define streamline flow, Bernoulli's principle, and we will also see the how in water, liquid or in gas, we can apply this principle and make our life easier because if the 70% of earth is covered with water, we must know how to operate in water. How does submarine operate? How does ship operate? And let's without wasting any time, let's get into it. In this chapter we shall study some common physical properties of liquid and gases. Liquid and gases can flow and are therefore called fluid. It is this property that distinguishes liquid and gases from solids in a basic way. Fluids are everywhere around us. Earth has an envelope of air and two-thirds of its surface is covered with water. Water is not only necessary for our existence, every mammalian body constitutes mostly of water. All the processes occurring in living beings, including plants, are mediated by fluids. Thus, understanding the behavior and properties of fluids is important. How are fluids different from solid? What is common in liquid and gases? Unlike a solid, fluid has no definite shape of its own. Solids and liquids have fixed volume. Whereas a gas fills the entire volume of its container, we have learnt in previous chapter that volume of solids can be changed by stress. The volume of solid, liquid or gases depends on the stress or pressure acting on it. When we talk about fixed volume of solid and liquid, we mean its volume under atmospheric pressure. The difference between gases and solids or liquids is that for solids or liquid, the change in volume due to change in external pressure is rather very small. In other words, solids and liquid have much lower compressibility as compared to gas. Shear stress can change the shape of solid keeping its volume fixed. The key property of fluids is that they offer very little resistance to shear stress. Their shape changes by application of very small shear stress. The shearing stress of fluids is about million times smaller than that of solid. Now, pressure 10.2. Stress means mainly the pressure. What the pressure can change the shape, size, and volume of the object. So, whenever we are talking about stress, we are referring to the pressure because stress is also F by A and pressure is also F by A. A sharp needle, when pressed against your skin, pierces it. Our skin, however, remains intact when a blunt object with a wider contact area, say the back of a spoon, is pressed against it with the same force. If an elephant were to step on a man's chest, his ribs would crack. A circus performer across whose chest a large, light but strong wooden plank is placed first is saved from this accident. Such everyday experiences convinces us that both the force that it covers area are important. Smaller the area on which the force acts, greater is the impact. This impact is known as pressure. It is saying just in the last section is just saying that when we pierce with a needle, it will pierces our skin. But and if the elephant stand on the human body chest, the chest would crack. But but here is the point: if we place a plank on the chest of the human body, and then elephant will stand, like the performer do in circus, then the chest would not crack. And this shows that the force is not acting on a small surface. That's why chest doesn't crack. It is acting on the large area of plank, so the force is distributed. When an object is submerged in a liquid at a rest, the fluids exert a force on its surface. This force is always normal to the object's surface. This is so because if there were a component of force parallel to the surface, the object will also exert a force on the fluid parallel to it as a consequence of Newton's third law. This force will cause a fluid to flow parallel to the surface. Since the fluid is at rest, this cannot happen. Hence, the force exerted by fluid at rest has to be perpendicular to the surface in contact with it. This is shown in figure 10.1. It's just saying that the force in the fluid is perpendicular to the surface. It is not the parallel to the surface, because if it is parallel to the surface, the suppose it is a parallel. Let me take the pencil and show that. Suppose this is a object shape, and if the force is parallel to the surface, suppose it is going upward or downward, anyway, so there will be, according to Newton's third law, it will apply another force, the downward, and hence there is a fluid uh, in the liquid. But it is not so. It is means it is a still. So that is not the case. The any other direction the force can act is the perpendicular to it, and that's what happened in the fluid. The fluid exert pressure perpendicular to the surface. Not any component is parallel to the surface, because if you take any other direction, it has a component parallel to the surface, and that we know that it is not the case, because fluid is not flowing. It consists of an idealized form of one such pressure measuring device is shown in figure 10.1b. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. This device is placed at the point inside the fluid. The inward force exerted by the fluid on the piston is balanced by the outward spring force and is thereby measured. Like if we put it inside any liquid, the force that will apply is perpendicular to the surface, and as a result it will also, the spring will also apply the force, and the point at which it is balanced is the amount of force that it can compensate. As we know the area, that we can calculate the pressure using it. The force exerted by liquid in the beaker, this is the diagram of the first case, and this is the idealized device for measuring pressure. If F is the magnitude of this normal force on the piston of area A, then average pressure P average is defined as the normal force acting per unit area. P average equal to F by A. Now in principle, the piston area can be made arbitrarily small. The pressure is then defined in a limiting sense as P equal to limit del F by del A, limits del A tends to 0. Their area, if we take infinitesimal small area and we apply this will become differentiation, as we know that from the differentiation and limit concept. Pressure is a scalar quantity. We remind the reader that it is a component of the force normal to the area under consideration and not the vector force that appears in the numerator in equation 10.1 and 10.2. Its dimension is ml minus 1 t minus 2. It has the same dimension that of stress. We know that. The SI unit of pressure is Newton per meter square. And the one thing good about dimension analysis, if two things has the same dimension, its impact on the object is, if you try to analog with the another concept, you can easily relate it. Its dimension is same, its unit is same, so it is also the force by area. It has been named as Pascal, PA, in honor of the French scientist Blaise Pascal, 1623 to 1662, who carried out pioneering studies on fluid pressure. A common unit of pressure is the atmosphere at atm. That is, the pressure exerted by the atmosphere at the sea level is 1 atmospheric pressure equal to 1.013 into 10 to the power 5 Pascal. This is the most important formula, and you should remember this conversion, 1.013 into 10 to the power 5 Pascal. Another quantity that is indispensable in describing fluid is the density rho. For a fluid of mass m occupying the volume v equal to rho equal to m by v. This formula we have known from many years, from last 4 to 5 years, from class 7 I think the definition of density is start. So it is mass by volume. The dimension of density is ml minus 3. Its SI unit is kg per meter cube. It is a positive scalar quantity. A liquid is largely incompressible and its density is therefore nearly constant at all pressure. Gases, on the other hand, exhibit a large variation in density with pressure. The density of water at 4 degrees Celsius 277 Kelvin is 1.0 into 10 to the power 3 kg per meter cube. The relative density of substance is the ratio of its density to the density of water. So this is the reference point. Whatever the density of water at 4 degrees Celsius, we compare relative density with this weight and we get it. It is a dimensionless positive scalar quantity. We are talking about relative density, not density. It is density compared to relative density. Suppose this is relative density equal to density of that material compared to density of water at 4 degree Celsius. Water at 4 Kelvin. You write 4 Kelvin. The density of some common fluids are, for example, the relative density of aluminum is 2.c. Its density is 2.7 into 10 to the power 3 kg per meter cube. The density of some common fluids are displayed in the table 10.1. At STP, fluid, water, seawater, mercury, ethyl alcohol, whole blood. Here and it is given in the form of this. Air is compared to 1.29, oxygen 1.43, and hydrogen 9 into 10 to the power minus 2. And interstellar space has very less density. STP means standard temperature 0 degrees Celsius and 1 atm pressure. STP is the condition under which we perform the measurement. Now the two thigh bones femurs has a cross sectional area of 10 centimeter square. Support the upper part of the human body of mass 40 kg. Estimate the average pressure sustained by the femurs. Total cross section area of femurs we can give 2 into 10 because there are 2 femur bone. The force acting 4 kg weight we multiply into G, we will get 400 Newton. 40 into 10, 400. This force is acting vertically down and hence normally on the femurs. Thus the average pressure is P average equal to F by A. So we will multiply 400 by 20, we will get 2 into 10 to the power 5 Newton per meter square. Pascal's law. The French scientist Blaise Pascal is observed that the pressure in a fluid at rest is the same at all points if they are at the same height. This fact may be demonstrated by in a simple way. Proof of Pascal's law: A, B, C, D, E, F. These are the surface A, B, C, and D, E, F. Is an element of interior of a fluid at rest. This element is in the form of a right-angled prism. This element is small so that the effect of gravity can be ignored, but it has been enlarged for the sake of clarity. Suppose that this is a very small object, but for the sake of clarity, we have shown it big. Why we have taken this small? Because we can almost treat as the same height. Same height means same pressure. This is a Pascal's law. If in fluid we are calculating the pressure at the same height, we will get the same pressure. And this concept, if you just remember, this chapter is over. This is a very important concept, and this is the basic on which the fluid dynamics or fluid mechanics will stand. Figure 10.2 shows an element in the interior of fluid at rest. This element ABCD is in the form of right angle prism. In principle, this prismatic element is very small, so that every part of it can be considered at the same depth. As I mentioned, we will ignore the height, that there is a height difference between one surface or one point of the prism to the another point. This is a very small surface. From the considered to be same depth from the liquid surface, and therefore the effect of gravity is the same at all these points. But for clarity, we have enlarged this element. The forces on this element are those exerted by the rest of the fluid, and they must be normal to the surface of the element, as discussed above. Thus, the fluid exerts the pressure Pa, Pb, and Pc on this element of area corresponding to the normal forces Fa, Fb, and Fc, as shown in figure 10.2 on the faces BEFC. Here BEFC, BEFC, this is the Fa, this is Fb, and on the corresponding surfaces. An area is also given. So the Fb sine theta equal to Fc. Fb and sine theta, if we take its component is Fc. This is this force will be, because sine this is a vector, all three are vector quantity. So this is Fb sine theta, then this will become this, and Fb cos theta equal to Fa. And AB sine theta is also given. AB sine theta equal to AC. Area will be the same. We can do by geometry, and this will be by equilibrium, because force acting on the infinitesimal small surface is 0. So this will balance out. These forces must balance out each other. So if we do Fb sine theta by AB sine theta, we will get Fb by AB. Sine theta is cancel out, and Fc by AC. Similarly, we can do for Fa also. We take the cos theta and we will calculate, and we will get the Fa by Fb equal to Fb by AC by Fb by AB. And this indicates that pressure at all points are equal. Hence, pressure exerted is small in all direction in fluid at rest. It again reminds us that, take other types of stress, pressure is not a vector quantity. It is another kind of stress. It is a bulk stress, you can call it. No direction can be assigned to it. The force against any area within or the bounding a fluid at rest and under pressure is normal to that area, regardless of the orientation of the area. Now consider a fluid element in the form of a horizontal bar of uniform cross section. The bar is in equilibrium. The horizontal forces exerted at its two ends must be balanced, or the pressure at the two ends should be equal. This proves that for a liquid in equilibrium, the pressure is same at all points in a horizontal plane. Suppose the pressure were not equal in the different part of the fluid, then there would be a flow, as the fluid will have some net force acting on it. Hence, in the absence of flow, the pressure in the fluid must be same everywhere in a horizontal plane. It just say that if we have this container, and this is the point at the same level, same horizontal level. Suppose this 4, then at this all 4 point A, B, C, D, suppose you take, then the pressure at these all 4 points are same. And if you take another point at the same another horizontal, this pressure is different, definitely different from this. If the fluid is static, but the fluid at all the same horizontal level is the same. And now we will stop this lecture here. There are only two concepts involved here, that the pressure at the same horizontal surface is the same, and also if there is a net force, then there would be a flow, and if there is not flow, then there is a no net force. So we will stop here. Thank you for watching this lecture.